In this video, we will compute a triple integral by switching to spherical coordinates. So we're integrating the function x squared, and the region is in between two spheres, and it's just the top half of those spheres. It's above the xy plane. So to switch to spherical coordinates, remember that in spherical coordinates x is the same as rho sine phi cosine theta. So we have x squared, and dv becomes rho squared sine phi d rho d theta d phi. Okay, now we just have to set up the bounds on the integral, so we have to describe this region E in spherical coordinates. So it's in between the spheres of radius 1 and 2, so rho goes from 1 to 2. It goes all the way around, so theta goes all the way from 0 to 2 pi, but it's only the top half of the spheres. It's above the plane z equals 0, so we don't want phi to go all the way from 0 to pi. We only want to go halfway, so phi only goes from 0 to pi over 2. Remember that phi equals pi over 2 is exactly a 90-degree angle, so that's the xy plane. Okay, now we just need to expand everything out and finish computing the integral. So we get a rho squared from the first part and a rho squared from the differential. So all in all we get rho to the fourth. Let's see, we get a sine squared of phi from the parentheses and a sine of phi from the differential. So we get sine cubed of phi, and we have cosine squared of theta. And the order we set it up was rho, theta, phi. Okay, for the first integral, when we integrate rho, the antiderivative of rho to the fourth is 1/5 rho to the 5th power. So that integral will just be 2 to the 5th minus 1 to the 5th over 5. 2 to the 5th is 32. 1 to the 5th is of course 1, so that's just 31 over 5 for the first integral on the variable rho. Okay, next we have to integrate theta. So we keep ignoring the phi for now. Pretend it's a constant. We're just integrating cosine squared. And remember what the trick is there. We use the trig identity that cosine squared is 1/2 1 plus cosine of 2 theta. So we'll put the 1/2 out front. And replace this with 1 plus cosine of 2 theta. Okay. So, let's do this integral. The first term, when we integrate 1, we just get 2 pi. And the antiderivative of cosine 2 theta is 1/2 sine of 2 theta, and we have to evaluate that from 0 to 2 pi. But this is of course just 0. When you plug in 0 and 2 pi, you get 0 both times. It's just 0 minus 0. So really we just have this 2 pi here. And that's a constant, so we'll just bring it out front. So we have 31 over 5 times pi is the constant out front now. And now we're to the last part. We're just integrating phi now. And we have to integrate sine cubed. And remember what the trick is there. It's to write sine cubed as sine squared times sine. And then use the trig identity that sine squared is the same as 1 minus cosine squared. And now we can do a u substitution. U equals cosine phi. And so du will be minus sine phi d phi. So let's see, what does this become? We have sine phi d phi. We need an extra minus sign. So we'll absorb that minus sign into the parentheses here by just switching the subtraction. So instead of 1 minus u squared, I'll write it as u squared minus 1. That'll account for the minus sign. And let's see. When phi is 0, u is cosine of 0, which is 1. And when phi is pi over 2, u is cosine of pi over 2, which is 0. And now let's actually add another minus sign, because the bounds look kind of silly this way. We have 0 on top and 1 on bottom. Let's flip them and get an extra minus sign. So we'll put the subtraction back the way it was before. Oops, I forgot something. If you'll notice, back in this step, I forgot to write the pi as we moved on. So I should be carrying this constant pi in front of the integral. Okay. So, if we do this integral, the integral of 1 from 0 to 1 is just 1. And the integral of u squared is u cubed over 3. From 0 to 1, that's just 1/3. And so this is just 2/3. So this ends up being 62 over 15 times pi.